Hey gang, how you doing? I'm Matt. As promised, this is your potential science objectives video. It's going to be awesome. I guarantee you that it's going to be incredible. You're going to talk to your friends about it. Anyway, today's video we're going to cover just some ideas for science objectives. It's potential science objectives. Just think of this as a menu, and you can choose different things off the menu. You can combine different things off this menu, or you can choose nothing off this menu. You can choose something else. You can make up your own science objective if you want. You have to choose something. You have to come up with some science objective, but you can choose from this. You can come up with your own, whatever you want to do. This is just some ideas to get you guys thinking, and also to let you know if sort of the range and the level of science objectives that we usually do in InSPIRESS, because y'all never done this before. If you do go off menu, if you do think of your own science objective, please talk to your teacher about it, talk to me about it, and we'll make sure that it's something that you guys could achieve this semester. Anyway, without further ado, the outline for today. First, we're going to go over the baseline mission, and I'll explain what that means when I get to it. We're going to talk about planet Venus a little bit more. We've also talked about it in class some, but we're going to go a little bit more in depth. Potential science objectives. I have them broken into 4 major parts, and it goes kind of outside in. So there's outside Venus, then the atmosphere of Venus, the surface of Venus, and then the core, inside the subsurface of Venus. And then also I have these 2 extra ones, temperature and heat flow, because there's lots of different temperature type measurements. I want to explain how temperature measurements work, and then also magnetic field measurements, because a magnetic field can be sort of anywhere. And then what's next, what you guys should be doing next, and then I'll give you an example science traceability matrix and talk a little bit about that. I'm going to try to keep this video short. We'll probably break it into a couple of videos just to make it more manageable as far as distribution and YouTube and whatnot. But I'd recommend that you watch both halves of the video at least once, and then if you have questions or if you want to focus on something, you can go back and watch those certain parts of the video. Also, this presentation should be online. Follow along with the presentation, because you probably can't read the slides from over this video. I'm sure the resolution's not that great. So download the presentation. It should be on the downloads page and with the video, or just ask me for it. But you want to follow along with this presentation. So the baseline mission. What is the baseline mission? In a nutshell, the UAH teams, their missions are going to be different from each other. We've got 3 different teams at UAH right now, and their 3 missions are going to be different. Not only that, their missions are going to change during the semester and during both semesters. And we don't want to put you guys through that type of chaos, basically, because it is kind of chaos. And so what we've done is we've designed what we call the baseline mission. This is the mission that you guys will design your payload for, because this is sort of a common denominator type mission that the UAH teams will, for the most part, satisfy. So you design to this mission. Don't worry about the exact details of the UAH mission. And if they say something, if the UAH team says something, just say, hey, this is the baseline mission that we were given, and we're designing to it. So don't worry about that. And if they give you a hard time, just send them to me. We'll take care of it, drop an elbow on them, something like that. Anyway, so getting to Venus is relatively easy as far as trajectories are concerned. It's just inside Earth a little bit. So we travel from the Cape, 160-day cruise, get to Venus. Once we get to Venus, this is not to scale, by the way. Once we get to Venus, we do something called aerobraking, which is where we circle around, because Venus is going around the sun a lot faster than Earth is. Venus is going around the sun. Venus travels around the sun once. It takes Earth 365 days to go around the sun. It takes Venus 225 days. So Venus is going faster around the sun. So we have to speed up to get to Venus, to catch up to Venus. But then we have to slow down in order to capture an orbit around Venus. So it's a speed up and slow down type situation. So in both cases, the speeding up and the slowing down involve propellant, and the propellant is mass. However, there is something on planets with atmospheres. There's something you can do called aerobraking. Basically, it's slowing down, and as you add each time you pass by the planet, you sort of dip into the atmosphere, and you use the atmosphere to slow you down. It's kind of like just dragging yourself. And so the first pass, you come out here and you drag. The second pass, you get lower. and lower and lower. And eventually, after 6 months of aerobraking, you're in a circular orbit around Venus. And the details are on the slide. So it's a 160-day cruise to Venus. It's a 6-month aerobraking. It's a 300 kilometer by 40,000 kilometer aerobraking maneuver. However, we end up in a 230 kilometer circular orbit around Venus. That's what I would focus on for you guys. This 230 kilometer circular orbit. It's a great orbit. It's just on the edge of the atmosphere of Venus, and we'll be in that orbit for a total of 4 years. 2 years primary, 2 years extended. So you can count on 4 years in orbit around Venus at 230 kilometers. There's multiple things to, multiple spacecraft, multiple mission elements to choose from when you're at Venus. There's not just an orbiter, okay? This is key. This is what you guys, because you guys get to choose which element you're going to be on. So there, well, first I'll talk about the mission objectives. So the baseline mission objectives, these are the UAH. This is what UAH is doing, okay? These are what their mission objectives will be. Your mission objectives, your science objectives can be whatever you want. However, their mission objectives are going to be one of these, all, some or all or one at least of these. What does the Venus greenhouse tell us about climate change? Venus has a huge greenhouse effect, and we want to learn about Venus's greenhouse effect so that we can look at Earth and see if Earth's going in that direction. That's a big deal, because Venus is kind of like, Venus is like Earth run amok, basically. And so we want to look at Venus and see if there's anything we can learn about the future of Earth from Venus, because we don't want Earth to end up like Venus. Venus is not inhabitable. How active is Venus? Volcanic eruptions, weather, stuff like that. How active is it, basically? When and where did the water go? We think there should have been water on Venus. That should have been there. Atmosphere, oxygen was there, nitrogen. It's a lot like Earth in a lot of respects. Where did the water go? When did it leave? We want to know this. And then, is there life on Venus? It sounds weird, but there's potential for life in the clouds of Venus. Not on the surface, not like running around, but sort of, things floating in the clouds. Small life, not like, people floating around like, hey, how are you doing? No. It's very, very small life, but and maybe not like life that we know. Maybe not life that we're familiar with. Probably not like that at all. Probably really tough life, to be honest with you. But there's the potential for life on Venus as well. Now, the mission elements, as I said, there are 3 different mission elements that you guys can have your payload on, okay? I just want to make this clear. Your payload can be on any one of these 3, or you can put your payload on a couple of these, or all 3 of these if you want. So you can be on any one of these 3 things I'm going to talk to you about, on any 2 of them, or on all 3 of them. However, you don't get more mass. You still get your 5 kilograms, you still get your box of paper, you don't get more mass and volume. If you divide it into 2 things, then the sum of the 2 things is 5 kilograms. If you divide it into 3 things, the sum of the 3 things is still 5 kilograms. You don't get more mass, you don't get more volume, but you can put it on any 1, 2, or 3 of the elements, okay? So the first element, like I told you, there's an orbiter, and it's got the transit to Venus, 160 days, and it does the aerobraking, like I said, but then it ends up in this 230 kilometer circular orbit around the surface of Venus. So from the surface of Venus, 230 kilometers up, and it's going around Venus for 4 years. There's going to be a balloon system. There's actually going to be 2 balloons going around Venus. These balloons are going to drop to an altitude of 55.5 kilometers, so around 55, between 50 and 60 kilometers, basically. And they're going to float. This is the picture of the balloon. This is the orbiter, by the way. This is the balloon. These are just, kind of renderings of it. This is the balloon, and it's going to be around 50 kilometers is a neat place on Venus, because that's where the pressure and the temperature are a lot like Earth. So that's cool, and it's really neat. So if they built something to survive at 50 kilometers up on Venus, then it wouldn't have to be that robust. There is sulfuric acid at 50 kilometers altitude, so there's that. But the temperature and the pressure aren't that high at that altitude. And then there's going to be 2 landers, okay? The landers are going to be really robust, really heavy-duty landers. The way they're going to descend, they're going to have an hour. It's going to take them an hour to descend through, the 230 kilometers. They're going to come down an hour and they're going to take data as they descend, but it's going to take them an hour because the atmosphere is so thick. Once you get toward the surface, it gets even thicker and denser. So this is another rendering of what the landers might look like. And then once they get to the surface, each lander is only going to last for 5 hours because that's all that they can last, because it's just so tough. It's so hot and the pressure is so high on Venus. 5 hours is the maximum. So again, you guys, your payload can be on the orbiter. It can be on the balloon system. There's a big balloon. Down there is the balloon's payload, okay? The balloon's huge. So you can put your 5 kilograms in your payload on the balloon. You can put it on the lander if you want. Or you can put, 2 kilograms here, 2 kilograms here, and a kilogram here. Whatever you want to do, okay? But you have the option of the 3 different elements, okay? I want to make that clear. You can put it on any of the 3, all of the 3, whatever. So you have the orbiter, the balloon, and the lander. Everyone got it? No questions? Good. Okay, sweet. So overview of the planet Venus, real quick. We're going to talk about it in class some. I just want to make sure I went over some things real quick in case I didn't get to them in class. Okay, Venus, second planet from the sun. We know this. It's the hottest planet in the solar system. Has a severe greenhouse effect, which means that basically the heat is trapped. The cloud layer, the atmosphere is so thick, so dense that it just traps the heat, and it just continues and it spirals out of control inside the inside the planet. So the sun's rays come in and they bounce around inside and just heat the planet up, and it just kind of spirals out of control. Once it gets started, it's really tough to stop. The radius of Venus is 95% of Earth. So really close to the size of Earth. The mass is 82% of Earth, and the gravity is 90% of Earth. So something interesting to note is that usually you think of gravity as an attractive force between 2 masses, but the mass is 82% of Earth and the gravity is 90% of Earth. So why is that? That'd be an interesting question for a quiz. I don't know. I'll let y'all figure that one out. There's a really thick cloud cover. We've had over 30 missions to Venus. The Russians and the Americans. The Russians were the first. The Russians were the first at every planet, actually. A little footnote. But the Russians landed on the surface. They landed on the surface 2 or 3 times, I think. First time they tried, they didn't make it to the surface because they didn't anticipate how thick the atmosphere was as you descended to the surface. Anyway, the reason, and this is what was really cool, the reason that there were so many missions to Venus is that way back in the day, way back when in the early days of rocketry, the early days of the space race and stuff, scientists actually thought that beneath the cloud layer of Venus it was going to be like a jungle. I don't know if they thought there would be animals there, but they thought it would be like really thick vegetation because they saw this planet out there and it had this really thick atmosphere, and it was close. It was about the same distance from the sun as Earth was. And about the same size, same gravity, so they figured, hey, it's got to have thick vegetation with all this cloud layer. It's got to have all sorts of stuff under there. When they finally got the first pictures back, I got some pictures in the presentation. You'll see there's no vegetation at all. But they actually thought, the scientists and at the time, people thought there would be jungles underneath the cloud layer of Venus. But we just couldn't see through the cloud layer because it was so thick. And so that's why we sent so many missions there. Because they wanted to see, early days, it was a closed planet. It's not hard to get to. There's a launch window it happens very periodically. So, and they thought I don't know if they thought they'd find life there. It would be very cool. So the orbit of Venus's orbit is probably one of the strangest or the strangest in the solar system. And also scientists don't know why it orbits the way it orbits. So there's something there if you want to think about that. Now, as I said before, Venus goes around the sun. Venus travels around the sun. It takes it 225 Earth days to travel around the sun. Now, if you were to look down on the sun, if you were to go and look at the North Pole of the sun, and look down on the sun, and just get really far away, obviously, and you can see the whole solar system from there. Every planet in the solar system goes around the sun in a counterclockwise fashion. Okay. So they go around the sun in this fashion, counterclockwise. So every single planet goes around the sun that way. Every single planet except for Venus rotates also in a counterclockwise fashion. So as they're going around the sun, they rotate in the same way. So it's almost like they're rolling along their orbit, okay? Each planet, except for Venus. Venus rotates around its own axis in the opposite direction as it goes around the sun. So it's like Venus is skidding around it's skidding around its orbit, if you want to look at it that way. Very strange orbit. It actually ends up doing some really weird things to the day cycle. And scientists don't know why. They have no idea why. It's called retrograde. That's spinning the opposite direction of its rotation. It's called retrograde. It's the only planet in the solar system that does that. So that means, because it spins in the opposite direction, and it also, check me on this, but I'm pretty sure it's the slowest rotating planet there is. It's very slow. Venus turns around its own axis. So it's really slow, basically, okay? So the solar day from high noon to high noon at Venus, if you were to take a single spot from high noon to high noon at a single location, it's 117 Earth days, all right? And so that's not a complete, that's just shy, that's a little bit shy of a year on Venus. However, there's something else called the sidereal day. And it looks like it's pronounced sidereal. And when as a good Southerner, when I first saw it, I said, it's the sidereal day. What's the sidereal day? It's called sidereal because, it's astronomy and it's kind of hoity-toity. Anyway, the sidereal day, which I'll explain in a second, it's 243 Earth days. So it's actually longer than a year, okay? Now, so what is a sidereal day? Here I have a little sketch. I just happen to have a sketch for you. So if you were to take a planet and take it away from the sun, take it just all by itself, and put it in a fixed coordinate system, and watch a single point of that planet and watch it rotate around, and get back to the same point. So one single point, like on the equator, rotates around and gets back to the same point. That is a sidereal day. On Earth, the difference between the solar day, between one point on Earth having high noon and back to high noon, and then one point doing this on Earth, is just 4 minutes. The difference is just 4 minutes. So it's not noticeable really on Earth because Earth spins and it goes in the same direction it's spinning. Because Venus spins the opposite direction it's rotating, it's the retrograde planet, it makes its solar days shorter than what they should be, okay? Venus spins so slowly. It should, if it spun that slowly in this direction, then its solar days would be much longer, but that's not the case. So there's two types of days that we measure. When we think of a day, everyone thinks of a solar day. However, when we think of a planet rotating around, making a one clear rotation, we also think of that as a day. And on Venus, they're completely different because Venus because Venus spins, because Venus orbits in retrograde, all right? Now, we'll talk more about this in class because it's really just like, I don't get what he's saying. But we'll talk more about it and everyone will understand it. I just want to bring that up. And again, this is one of those things that scientists don't know why Venus does this. They have no clue why. I have no idea how you could discover why it did it because it's been doing it as long as we know it. However, it's just one of those really weird things about Venus. So Venus is inclined. I don't know if y'all knew this, but the sun, if you were to take all the planets in the solar system, they pretty much go around the sun in a single plane, okay? Basically around they spin around the sun at about the sun's equator, essentially, because that's where this big mass of the sun spinning around, okay? So that's called the ecliptic plane. Most planets are pretty close to the ecliptic plane. Earth's in there. Venus is inclined 3.5 or 3.4 degrees above or below the ecliptic. So it goes up and then it goes down. It goes up and down. And what that does is it makes the distance between Earth and Venus a lot different at times. The shortest distance is the distance is huge. The average distance between Earth and Venus, if Earth were a tennis ball, if Earth were the size of a tennis ball, Venus would be about the size of a cue ball, just a tiny bit smaller, okay? But the distance between the two of them would be 2 football fields, like 220 yards. So let that just kind of sink in. There's a long distance between us. And But as we've said in class, I think multiple times, it's the brightest object besides the sun and the moon. The brightest object in our sky, you can see it every morning and every evening. It's called the morning star and the evening star. The sidereal day. Okay, the solar wind. Venus is closer to the Earth. Sorry, Venus is closer to the sun than the Earth is, and it has no magnetic field. Scientists don't know why. Scientists think that Venus should have a magnetic field. They don't know why it doesn't have one. Or at least, let me say it this way. We've never measured Venus's magnetic field, its own magnetic field. So it's possible that there is one, we just haven't measured it well enough yet, okay? So I want to clarify that. So if it has one, it's very, very small. It's very, 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 very weak. So what that does to Venus is it allows the solar wind, the sun kicks out a bunch of, basically it's like photons and charged particles and whatnot, we call it the solar wind. And Earth's magnetic field protects us from those things. That's why we don't die. Venus pretty much gets pummeled by it, okay? It kind of does all this garbage around Venus and steals. What it does is it steals some elements away from Venus in the upper atmosphere. It just kind of pummels the upper atmosphere of Venus. And it erodes the elements from Venus. And it's a really interesting effect, and it's something that y'all could look at. We'll talk about in a minute as well. The atmosphere of Venus, it's a really thick atmosphere. Earth, just to give you a reference, the atmosphere is approximately 250 kilometers up. The clouds go up to 200 kilometers. The cloud deck on Earth, the highest clouds that we have might be 15 kilometers. Most clouds most of Earth's atmosphere, 70 or 80% of Earth's atmosphere is below 11 kilometers. A plane flies at about 30,000 feet, which is, it's like 6 miles, which is about 10 kilometers. And there's atmosphere above it, but there's not that much left. And you're above the cloud deck when you're on planes typically too. So Venus's atmosphere, very, very thick. Venus's atmosphere is basically all carbon dioxide. It's 96.5% carbon dioxide, 3.5% nitrogen, and then other stuff, oxygen and some stuff like that. The really funny thing about it is the amount of nitrogen that's in Venus's atmosphere almost equals the amount of nitrogen in Earth's atmosphere. Earth's atmosphere is around 78%, 72%, something in there, 77% nitrogen, okay? Earth's atmosphere has a lot of nitrogen in it. Venus's atmosphere has almost the same amount of nitrogen, but it's got so much more CO2 that the percentage is lower, okay? So what's really interesting though is that if you took all the CO2, Earth has CO2, we have carbon dioxide, and it's in our soil, it's in our rocks and stuff, okay? But if you took all the carbon dioxide that we have in our rocks and you boiled it off, you outgassed it and put it in the atmosphere, Earth's atmosphere would look a lot like this. It would have about this much carbon dioxide and this much, and then other trace gases. So the more you look at Venus and the more you look at Earth, the more similar they are. It's kind of scary. So that's what's some interesting stuff. That's why scientists are really interested in Venus right now, because of the greenhouse effect. They're like, oh my goodness, we hope this, we don't want this to happen on Earth because we're all dead. And the more we look at Venus, the more similar Earth and Venus become. Winds blow on Venus really, really fast. You got 100 meter per second winds and stuff like that, just whip around the planet. The winds blow 60 times the speed of rotation. Granted, as I said, Venus is slow rotating. It's the slowest rotating planet in the solar system, but still, it's ridiculously fast winds and weather because of the thick atmosphere, basically. Earth's winds are maybe up to 20% of Earth's rotation. And Venus has lightning storms, and there's huge cyclones. We'll talk about those in a minute. Huge cyclones at each of the poles, dual cyclones. There's some plots that tell, this is a graph. Look at this graph closer in the charts. It tells you the temperature and pressure of Venus as you descend through the atmosphere. Okay, we're started outer, then atmosphere, now we're at the surface of Venus. The surface of Venus, it appears that it was shaped by volcanic activity. However, scientists have never actually, there's no direct evidence of volcanoes. They've seen indirect evidence of volcanoes. They've seen, they've registered, they've measured sort of hot spots, not hot spots, but just spots with higher than normal intensities of sulfur and stuff like that. Like a volcano erupting, they've sensed that in the outer and in the atmosphere, but they've never actually seen or heard or whatever a volcano erupt on Venus. So that's That's neat. That's something you could think about, by the way. So the really other interesting thing is that as the surface of Venus appears to be 500 million years old, which in terms of planets is very, very young. I mean, planets are billions and billions and billions of years old, okay? But so what scientists think is that 500 million years ago, Venus had this dramatic resurfacing. Like basically, like every volcano on the planet erupted and just lava went everywhere and covered the entire planet. And then it solidified, and so the surface of the planet was brand new. That's what they think, basically. They call it a resurfacing. Basically, it's just lava coming out of all the volcanoes and making a new outer shell. At the surface of Venus, as we've talked about in class, the pressure is 93 times that of Earth's atmospheric pressure. Basically, it's 100 times Earth pressure at the surface. And the surface temperature is just shy of 900 degrees Fahrenheit. It's very hot, very high pressure. The surface across Venus, because of the thick cloud layer, because of the greenhouse effect, the surface is basically isothermal, which means scientists think it's the same temperature all around. There is some variation in temperature. They don't know why the temperature varies in different locations, but it varies some, and that's something you can look at as well. But for the most part, it's isothermal. It's the same temperature all the way around. These are some actual images from the Russians who landed on Venus. This is an artist. This is a colored, a radar image that they just put some false coloring on. It's some impact craters and whatnot. Now, the very interesting thing, and then another one of those blow your mind type deals, is that because of the temperature and the pressure near the surface of Venus, the carbon dioxide, the air at the surface of Venus, the air there, the gases at the surface of Venus are not gases. They are what's called a supercritical fluid. They're not a liquid, they're not a gas, they're a supercritical fluid. They're a thing, okay? I don't know how to describe a supercritical fluid to you. It still moves at the winds are very slow at the surface because it's so thick, the density is so high. But because the densities are so high, there's still enough momentum to move rocks and stuff. So because they did see this in some of the Russian images. 1 or 2 meters a second is how fast it moves. But it's not, you can't think of it like a gas like Earth. You can't think of it like water. It's almost whatever's between a liquid and a gas. Whatever that is, that's what's at the surface, okay? The density of air is, 1 kilogram per cubic meter. The density of water is 1,000 kilograms per cubic meter. The density of the CO2 at the surface of Venus is 65 kilograms or 68, somewhere, upper 60s. Kilograms per cubic meter. So it's a lot more dense than, it's 65 times the density of our air, but it's not quite a liquid like water. It's just really bizarre. So at the surface of Venus, it's probably more like swimming than it would be, moving through gases. So it's really weird. And we're going to have a hard time grasping that in our brains because I have a hard time visualizing and imagining what a supercritical fluid is. But we'll work on it, okay? So Venus' subsurface, gosh, I'm already taking a half hour, sorry. Venus' subsurface, we don't know much about Venus' subsurface at all. We've got some guesses, but that's about it. Because I'll talk about subsurface, later, how you determine what the subsurface is. But basically, they think it's magma down below, they don't know. Because of the surfacing, that's why they think that. Because of the resurfacing event, they think that there's magma down below. It's like a liquid core like Earth. They think it's a single plate covering the whole planet. They don't think there's individual plates like Earth has. So we have tectonics where the plates move and stuff. That doesn't exist. No plate tectonics, but they do have some sort of quakes. They think they've sensed some vibration and movement in Venus, but they're not sure why or what it is. So they call them quakes. So potential science objectives, I've grouped them into 4 major categories: outside Venus, atmosphere of Venus, surface of Venus, and then Venus subsurface. Okay, 4 major categories. We're starting on the outside and going down basically. So outside, atmosphere, surface, and then inside. So outside Venus, in a nutshell, you've got basically the biggie that there is they're the interaction of the solar wind with Venus. The solar wind, the sun just pummels Venus. It's just really, the sun is not nice to me. Venus has a rough life, okay? And the sun does not help Venus at all. So what it does is it creates a bow shock across Venus. I mean, just like you saw in those images, you know, there's like a shock wave, you know, around Venus. And you can measure that because behind Venus there's a trailing area of some low pressure, or higher pressure rather, sorry. And what this does, this solar wind, is it allows some of the lighter elements, like hydrogen and stuff, to be eroded out of the atmosphere on Venus. The solar wind just takes them, just carries them away, basically. So that's an interesting phenomenon that happens on Venus. It does not happen on Earth, fortunately. The atmosphere of Venus, probably one of the interesting things about Venus, because it's so thick and lots of stuff goes on in it, is there's basically two things you can measure in the surface and the atmosphere. There's basically, if you were to boil it down to the basics, there's just two things you can look at. There's properties and composition. Properties and composition of the surface, or properties and composition of the atmosphere. Now you can have a different size objective. You can say, I want to look for the cyclones. I want to study the greenhouse effect. I want to look for life in the clouds. I want to look at the acid rain, the precipitation, the jet streams, lightning. You can, look at all these things. But basically, what you're going to be doing is measuring some properties of the atmosphere, or measuring the composition of the atmosphere, or both. Okay. So your science objectives will be these things, but what you're going to actually measure will be, properties or composition. I just want to make that clear. Okay, that's why I've broken it down this way, because you're going to be measuring certain properties or measuring the composition. But I'll talk about what these things mean in a minute. But same with the surface. Your science objective could be, okay, we want to go to the surface and see if we can measure even a minute magnetic field. We're hoping for a magnetic field somewhere, because it doesn't make sense that it doesn't have one. Scientists don't know why it doesn't have one. We're looking for one. Soil mechanics, you can look at that. We're looking for volcanoes, but you're looking for properties or composition. The resurfacing, that's the properties of the surface or the composition of the surface. Again, this is all basically, you could boil any of these down to measuring properties or measuring the composition. The subsurface, there's two main categories for the subsurface. You can look at internal structure. Does it like Earth? Earth has the core, the mantle, the crust. A lot of planets are like that. Is Venus like that? We don't know anything. We don't know much at all about Venus's internal structure. We'll talk about how that works in a minute too. There's also something called heat flow. On Earth, we have this really hot core, and then the heat kind of flows out to the surface, And so you can look at, all planets have heat flow. Moons even have heat flow. So you can look at the heat flow of the different planets. It tells you a few things. It tells you what the material is made of, if it's conductive, how well it conductive is. And then you can also see, does the temperature increase or decrease as you get deeper? Okay, so we're going to start with outside Venus and then work our way down. So we're outside first, and then atmosphere. Excuse me, I'm very sorry. And then surface. So we're outside Venus first. So the interaction of the solar wind. This is a graphic. It's obviously just an artist's rendering of it, but it's a really neat one, I thought, because it shows, here's the sun, here's Venus, okay, and here's the Earth. Earth has this awesome, really strong, actually, for the size of our planet, magnetic field. And that's what saves us a lot, our magnetic field. As you can see, the solar winds come and hit, and our magnetic field pushes them away, and we have this big, effect. That our magnetic field saves us from the solar wind plummeting us, just pummeling us. So I can't speak today. So now Venus has no, or at least that we've measured, magnetic field of its own. It has an induced magnetic field. It's induced by the solar winds. We'll talk about that later. But so basically, Venus just gets pummeled by the solar winds, and it steals elements away from Venus. So you can look at that. Here's a closer version of it. So the solar winds hit it. This is what we call the bow shock across the front of it. And then it steals the elements away. They just kind of get pulled away. Some of the lighter elements that are on the outer part of the atmosphere. So if you want to look at outside Venus, the solar winds, that would be interesting to look at. So for the next part, I'm going to talk about the atmospheric and surface measurements, because you got properties and composition for each of those. So there's the two basic types of measurements. There's properties and composition, like I talked about. The science objectives, you could look at, you could look at life, you could look at volcanoes, you could look at precipitation or whatever. But they basically boil down to properties and composition, okay? And so properties are qualities of the atmosphere or surface. Examples are pressure, temperature, density, viscosity, charge, pH, which is a measure of acidity, wind speed, humidity. Now composition are the constituents of the atmosphere or surface. What is it made of? Does it have CO2? It has lots of CO2, right? Does it have, how much oxygen is in this area? How much nitrogen is there? Is there carbon just by itself, elemental carbon, not carbon dioxide? So examples of the elements, you can look for compounds, ions, salts, acids, bases. It's kind of similar to that, but you can look for specific acids and bases. Minerals, metals, and biologicals. Ooh, biologicals are the fun one, right? If you're looking for life. Now for the surface only, you wouldn't do this in the atmosphere, but for surface only, you can look at soil mechanics. You can basically, penetrability, hardness, that type of thing. There's no hardness to an atmosphere. That's why it doesn't apply to atmosphere, but you can hit it with something and see how the soil reacts. We haven't done that yet on Venus. We've only set a few things down on Venus, and we've never done any soil mechanic measurements on Venus, as far as I know. So properties, remember there's properties and composition. So properties, pressure, to measure pressure, use a pressure probe. It's a touchy measurement, which means that the pressure probe actually has to touch what it's measured. The pressure, it has to touch what it's measuring. So if you have a pressure probe that wants to measure the pressure in this room that I'm in, then the pressure probe actually has to touch the air in the room. So might not sound like a big deal, but it's a big deal if the air in the room is 900 degrees Fahrenheit. So that's a big deal. Temperature, it's measured with a thermocouple. We'll talk about thermocouples at the end here. It's also a touchy measurement. The thermocouple, just like when you take your temperature, the thermocouple has to touch what it's measuring. Density, it's a mass and volume measurement. You can actually measure this one indirectly. You don't have to touch it. You measure mass and you measure the volume. You don't have to touch the things. You measure mass and volume, in enclosures without having to actually touch it. So that's nice about that. Viscosity, you can use viscometers or rheometers. You can also measure, viscosity can be measured as something falls through something. Now, Venus is a great example of falling through different densities of materials and different viscosities of materials, because as you go down, the density changes so much from upper atmosphere to lower atmosphere. So that would actually be a really neat thing to do. Just drop something and see how it changes its flight as it goes down. You can measure the density and viscosity as you descend. Charge, you're going to use an electrometer or galvanometer. It's a touchy measurement. Also, you have to touch it to measure the charge. And charges, positive, negative, and how positive and how negative. pH, the acidity or how acidic something is. It's an electrode, a pH meter, or there's indicators also. Also touch the fluid. Wind speed, usually an anemometer, which are those spinny things that you see on tops of weather chasing vans and stuff. That's an anemometer, those things that spin really fast. Or you can use an accelerometer. Now for a direct measurement, to measure it directly, use an anemometer, and it spins around. It actually touches, the wind moves the spinny thing. Now typically the anemometer has to be stationary, and the wind or whatever's you're measuring the velocity of moves the anemometer. An indirect measurement, you can use an accelerometer. The probe itself, it doesn't have to touch it this way. You can infer, using the accelerometer, you can infer, and we'll talk about that in a minute too, you can infer the accelerations of from the changing in directions, you can infer the wind speeds. Sorry. Humidity, you use a hygrometer. We typically measure temperature, pressure, and mass with this. Humidity, you can't just measure humidity by itself. You have to measure other things because humidity is a strong function of the other of temperature and pressure. And then precipitation, because it rains sulfuric acid on Venus. You can use a rain gauge typically, and a rain gauge is just like a cup essentially, right? And it has to face up. It has a direction to it. You can pour the water in, pour the rain in there. There's an opening. There's an orientation, and then typically you got to look at it, right? You got to look at it to do that, and that's difficult when it's when you're that far away. So, composition. Composition's usually measured by what's called a mass spectrometer. As the name would suggest, spectrometer, spectrum, and it's a spectrometer. It's pronounced spectrometer, but it measures a spectrum. It measures the spectrum from a mass, okay? So that's what it does, basically. It's an analytical technique that measures the mass-to-charge ratio of charged particles used for determining the mass of particles, elemental composition of the sample molecules, and the chemical structures of the molecules. It works by ionizing chemical compounds to generate charged molecules or molecule fragments and measuring their mass-to-charge ratios. What does that mean? Here's what happens, basically. So the basic procedure, a mass spectrometer. What it does is it shoots a laser, and a laser or an electron beam will hit whatever you want to measure, whatever you want to find the composition of. If it's a rock, if it's air, if it's a gas. It doesn't do liquids. It's gases or solids. So you've got this, say we got this silver thing, and you have a laser, and it goes, doo, it hits it. What happens is at the point where the laser or the electron beam hits the target, it ionizes that point. It gets really hot, and it ionizes the very, very, very small stuff at that point. And it forms charged particles when it ionizes. Okay, that's what ionize means. It forms charged particles. And these ions are separated according to their masses, because the faster ones move faster away, and the heavier ones don't move as fast. So they separate themselves naturally because of their speeds. But there's an electromagnetic field that's set up because of the electron beam that's hitting the material itself. Okay, and then ions are detected quantitatively method. Basically, they emit light. Okay, a spectrum. Okay, the laser hits it, and it ionizes this little point. These ions emit light, and this light is analyzed by a camera, a receiver, basically. Okay, so in a nutshell, laser beam hits something that you want to know. You've got this. You're like, what is this made of? And then you have a laser beam that hits it, and it emits a light. A lot of stuff happens in that millisecond, but in a nutshell, it emits a light. That light is seen by a sensor, and that sensor goes, oh, it's a napkin. But it says, no, actually it doesn't say it's a napkin. It says, oh, it's got carbon in it, it's got nitrogen in it, it's got so many different things in it, and it tells you what's in it. I'm sure most high schools actually have, in their chemistry labs and whatnot, they have mass spectrometers. So if you can ask your chemistry, physics teacher, whatever, if y'all have a mass spectrometer, and you can see how those things work. Maybe do an experiment with it to see how neat it is. There's two basic types, and these are my basic types. These are Matt's basic types. I've reduced it down to something I think is manageable. There's what I call, there's different variations, but what I consider the two basic types, there's an internal mass spectrometer and an external mass spectrometer, okay? The internal one, basically the substance that you want to measure, you put it into a box. And inside the box, all this stuff happens. The laser hits it in the box, and it emits a light inside the box, and the sensors inside the box, and so it all happens basically inside a box. That's the internal stuff. Those are really accurate, okay, as you would think, because it's it's fully enclosed and everything's controlled. There's what I call the external mass spectrometers, where it shoots a laser out into the air or whatever, out wherever it is. The laser shot out, it hits the ground or a rock or whatever, and then that rock or whatever emits light, emits its spectrum, and that spectrum is seen by a sensor that's over here, back near the laser, and then it determines the constituents. It determines the composition from there. So the external ones, they're a lot less accurate. They're easier to use, typically lighter than the internal ones. Because the internal ones, you got to get the junk into the internal ones somehow. I don't know how you're going to do that. If you're falling, you might just be able to have it fly into it. But so there's problems with the external one. It's easier to use, but they're not as accurate. And the internal one, much more accurate, give you better results, but they're more difficult to use and usually bigger. Internal usually weighs more. Yeah, okay. So bear that in mind. We'll talk more about this as we go along, but just bear that in mind. Now, properties of composition, the issues with it. Many measurements are touchy, okay? That means that they must come into contact with the thing they are measuring, okay? So temperature, to measure the temperature of my arm, I would have to touch my arm with a thermocouple. Okay, you just can't. I mean, they have those laser jobbies, you know, but those just don't work well at all, especially in space. We've never used those. The laser beam jobbies, those just don't work in space. So some properties can be inferred or measured indirectly. Viscosity and wind speed can be done that way. You can indirect measurement. Spectrometers are not robust. I didn't say that earlier. That means if you were to drop them, they'll probably break. They just aren't made to withstand, because there's a laser. There's a laser that has to hit something, and then there's a camera or a sensor that has to see this thing. If it hits, and if it hits, it has an impact, they can go like wonk, and you'll never see anything. So they're not robust. They're not made to put up with an impact. And there's a trade. Internal spectrometers are more accurate, but external spectrometers are easier to use and usually less massive, as I said before. Okay, so we did. Now I'm going to go over some things for Venus atmosphere, because we did properties and composition. Remember, properties and composition for this atmosphere or the surface. Basically, all these things can be measured using properties and composition, but I'm going to go over these anyway. So, lightning. This is not a picture. It's an artist rendition of lightning on Venus. They've got weather and lightning. They've never actually seen lightning or heard lightning or whatever. They've only detected waves, certain waves that are produced when lightning occurs. So that's why scientists think there's lightning. There's also lots of friction and charge, and they think there would be lightning, but they've never actually seen lightning or measured lightning. That would be interesting, because that would be a direct confirmation of what scientists think. And like right now, they're saying, okay, there should be lightning on Venus, and based on these waves that we've measured, there's some certain waves, you can look it up. These waves say that there was lightning at a certain point, but they've never actually seen it. The greenhouse effect, again, a big deal. That's where the temperature just kind of spirals out of control. That's a temperature. That's a properties and composition measurement. Cyclones. This is an interesting one. Okay, at the north and south pole of Venus, these are actual images from Venus. This is an image. Sorry. There are two counter-rotating cyclones at the north and south pole. Big, huge, not really hurricanes, but cyclones. Just big winds, and they counter-rotate and they spin. And they're right next to each other. And it's just crazy. Scientists don't know why they're there. They don't know what the purpose of them is. And there's obviously a lot of energy that needs to be released, or something's going on with the weather patterns there at Venus, the jet streams and whatnot that requires these cyclones. Here they are, the polar cyclones in this image too. You can see them. They're counter-rotating. Vortices is what they call them here. Polar vortices. And but it's just crazy stuff. That would be an interesting thing to measure as well. But again, if you measured it, you'd be measuring wind speeds and properties and composition of those things. Life in the clouds. Oh, sorry, jet streams was next. Jet streams. This is an image of the jet streams. This is what they think the jet streams are like on Venus. We've never sent a balloon around Venus to look at the jet streams before. So we don't know. This is what we think about Venus. We've never spent a lot of time in the atmosphere of Venus, enough time to figure out the jet streams. But they think they operate, basically they think there's one big jet stream for the upper atmosphere, then the lower atmosphere has another jet stream. So the upper atmosphere goes from, basically covers an entire hemisphere, and then the lower atmosphere, it's a quarter of a hemisphere, or a quarter of the planet. And then, Earth has one big jet stream that goes around it, basically, and then we got trade winds that go the other way. Venus has a lot of stuff going on because it's stacked jet streams as well, which is kind of funny. Earth is not. Earth's atmosphere, if Earth were the size of a globe, the atmosphere of Earth would be as thick as the shellac around the globe, just a globe to give you a reference on how thin Earth's atmosphere is. Because we don't need a thick atmosphere, because we have a nice magnetic field that protects us from the solar winds. So anyway, and Venus has to have a thick atmosphere because they don't have a magnetic field. Anyway, so life in the clouds, again, at around 50 kilometers altitude, as I was saying, the temperature and pressure on Venus are about like Earth. It's about 72 degrees Fahrenheit and 1 atmosphere of pressure, 14.7 psi. And so now granted, there's not much oxygen there. And that's also happens to be where the layer of sulfuric acid clouds are. But scientists do believe that there could be some life in near that altitude, just small particles or small microbes that just float around, and they could live off sulfur or something. It would be life that we wouldn't be familiar with, obviously, some sort of extremophile, but scientists believe that that's the case. And then the acid rain. Now the acid rain is interesting because it does rain. It does have sulfuric acid rain, but the rain does not reach the surface of Venus because it gets too hot and the pressure's too high. So basically, it's kind of like this. It'll fall a certain distance and then just evaporate back up. And so you've got this raining down and then evaporating back up. So that basically it rains at a certain altitude and never really hits the ground, because the ground is the temperature is so high and the pressure is so high as you get closer to the ground. It can't. The sulfuric acid rain can't reach the ground. But again, we've never measured precipitation on Venus. We've never measured where the raindrops are or where they occur or how long they go, whatever. There's lots of stuff to do there. The surface of Venus, this is an artist. This is a really, really, scary artist rendering of Venus. There's an astronaut in the middle of it. I don't know why they're there, but I just like the picture because it's kind of scary looking. I think of Venus as very scary. This is an actual photo. This is an image from one of the Russian landers. I don't know why they made these little jagged things on there, but so there's rocks down there. There's small rocks and kind of shale-looking rocks down there. There's you can find a few images online, all the images are online from the Russian missions. And again, Americans, we've never put a lander on Venus before. But anyway, so on the surface of Venus, you can look at soil mechanics. You could have something that hit the soil and measured how it slowed down. That's soil mechanics. You're measuring the hardness, measuring the penetrability of the soil, trying to figure out what it's made of. The landers that they landed and didn't measure how they landed when they landed. Magnetic field, again, it's possible that there's a magnetic field closer to the surface of it because the atmosphere is so thick. It's possible the magnetic field just doesn't get out that far. So as you descend, as you get closer to the core of Venus, it's possible that that it does have a magnetic field and it's just not that strong, and it's more the cloud layer prevents it from getting out, and so we've just never measured the magnetic field. Essentially, is what I'm saying. Possible it's still there. Again, there's volcanoes. Scientists believe there's volcanoes. They want there to be volcanoes. I want there to be volcanoes on Venus because it's cool. Okay, but we've never actually seen a volcano, never measured a volcano, never put a probe in a volcano. That'd be tough to do. It's a good shot right there. But that would be something you guys could look at. And the resurfacing, again, like I said, 500 million years ago, scientists believe that all the volcanoes on Venus, for some reason or another, erupted and put a brand new surface down. And that's why the surface of Venus doesn't appear to be older than 500 million years. And so getting down there, sampling the surface, trying to determine the real actual age of it, and seeing if there's a difference in different locations. That's the one thing too, is they say 500 million years ago. The uncertainty in that number is very high. It could, part of it could be 300 million years and part of it could be 800 million years, okay? So there's a difference. There's got to be a difference because it would take a long time to resurface an entire planet. And that's some interesting stuff right there to figure out what the difference is. Where did it start and where did it end? So scientists want to know this. I want to know this. So it's good stuff. So we're going to keep going.